Hello, good morning, one and all. Okay, uh, hi, very good morning, one and all. Today, we would like to look into uh, an important session called page replacement algorithm. So, before we go into page replacement algorithm, first let me tell you which is a part of virtual memory management. Till the last class, you might have understood the importance of paging and segmentation, demand paging, paging considerations. In today's session, we will look into an algorithms which helping us to swap in and swap out. So let us recap the session. Till the session, we have seen how a page is going to be divided into the virtual memory as well as in the main memory. So each page can be either stored in the secondary memory as well as stored in the main memory in the form of frames. So if you understand, there are two different types of memories. One is secondary storage memory, another one is main memory. So main memory we are considering as the frames here in our example, whereas in the secondary storage memory we are calling it as pages. So when exactly we are going for these page replacements? When there is a need of moving the data from secondary storage into a main memory, we are calling it as swapping in. Retrieving the data back from main memory to secondary memory, we are calling it as swapping out. So these algorithms helping us when exactly you would like to move your data from secondary storage into a main memory by replacing the existing pages available in the frames. So which frame need to be eliminated or called removed from the main memory by replacing with the new page which is coming into main memory from the secondary memory. These algorithms are going to be helping us. So let us see various types of algorithms that we are going to looking into it. So as I stated here, when the data located in secondary memory is needed, it can be retrieved back to main memory. The second point, process of storing data from main memory to secondary memory is called swapping out. Retrieving data back to main memory is called swapping in. We will see various examples here in our session by making you understand deep about swapping in and swapping out. Sometimes we call it as roll out, roll in, write in, write out. Like that, different terminologies we are using here. Only the point you should remember is from the secondary memory into main memory, when you are keeping the data, we are calling it as swapping in. So this diagram definitely helps you in understanding more about the page replacement algorithm. Consider this is a main memory, okay, and this is a secondary memory. So when you want to swap a page from secondary memory into main memory, you are calling it as swapping in. When you are replacing one page from these frames to a secondary memory, we are calling it as swap out. Okay, so this you have to understand very clearly. So obviously the page table is going to helping us to note down all the logs happening into the swapping with the help of page replacements, right? So let us see various types of page replacement algorithms, starting from FIFO, optimal, LRU, so on and so forth. There are many more page replacement algorithms. So we will look into one after other with a crystal clear example. Okay. The main goal of this page replacement algorithm is to provide lowest page fault rate. Again, what do you mean by page fault? If you want to understand the page fault as well as page hit with the help of a beautiful architecture, I would like to explain you exactly means of page fault. Okay, the process of moving the data from secondary memory into a main memory, we are occupying some space into the main memory, right? So we are considering that as page fault because you have replaced that page from secondary memory into main memory. That's the reason why you are calling it as page fault. So the algorithm that we are using, right, will help us in reducing the number of page faults. The less number of page faults becomes the more stronger algorithm. Okay, so let us see which algorithm brings a less page faults, right? So next thing, evaluate algorithm by running out it on a particular string of memory references. So we are using a terminology here called a reference string. Okay, so the reference string, let us say a sequence of numbers we are considering as an example here for representing a reference string. With the help of those reference strings, we are going to find out how many number of page faults are going to be occurred here. So if you see this algorithm, for example, you want to start the process, send a page request. When the page request is sent to a main memory, first of all it will check whether the concerned page which is looking forward to enter into the main memory is already available in the main memory frames or not. If it is already available, we consider it as a hit. We call it as hit. If that concerned page which is trying to enter into the main memory is not exist in that frame, we'll consider it as a page fault. Okay, so it will be fetch page, and finally the process is going to be stopped. This fetching from secondary memory into the main memory called as page fault. So let us see an example here. Yeah, as I discussed, we are trying to reduce the number of page faults by increasing the number of frames. What do you mean by frame again? A main memory is again going to divided into a slot called as a frames. Okay, when the more number of frames are available, the lesser number of page faults are going to happen. This is a general phenomenon. If you see the heading graph of a page faults versus the number of page frames, this vertical will be considering as number of page faults. Let us say 2, 4, 6, 8, 10, 12, 14, 16, and number of frames are 1, 2, 3, 4, 5, 6. Let us say when I have a frame size as 1, my page faults are 15, around 15. Okay, when I try to increase the frame size from 1 to 2, the number of page faults occurred during this page replacement are going to be reduced. See here, exactly you can find in between 8 and 6, so that is 7, we can consider it as. So earlier it was 15, now it is reduced to 7, right? And similarly, when I try to improvise the number of frames from 2 to 3, the number of page faults are going to be reduced because the more space we have to accommodate a number of pages into my main memory. So when I have this flexibility to swap in pages into main memory, obviously the number of page faults are going to be reduced because I can accommodate more number of pages into my main memory, right? So obviously when you keep on increasing the number of frames, the number of page faults are going to be reduced. This should be done, right? So let us see the various examples that we have in the coming slides. So let us start from the FIFO policy. So this is the first algorithm that we are using in the page replacement algorithm. So this FIFO policy is like this. Treat page frames allocated to a process as a circular buffer. When the buffer is full, the oldest page is going to be replaced first. Hence, first in, first out. A frequency used page is often the oldest. So, it will be repeatedly paged out by FIFO. So, the simple implementation of this algorithm is, so requires only a pointer that circles through the page frames of the process. So, let us start working out with an example given by this. Okay. So guys, we first consider it as a reference string. So this is a normal sequence of the numbers which we are considering as pages which are available in the secondary memory. Okay. That is 7, 0, 1, 2, 0, 3, 0, 4, 2, 3, 0, 3, 2, 1, 2, 0, 1, 7, 0, 1. This is a reference string. What we can consider it as? This reference string is considered as pages which are available in the secondary memory. Now what would I do here is, we are trying to swap in those pages into the frames. Again, what do you mean by a frame here? The frame is the slots of divided the main memory. Okay, so this is a main memory. We are considering it as a frame. What is the size of the frame here that I have? The size of the frame that I have is 3. See, this is 1, this is 2, and this is 3. Right? So I have 3 frames in my main memory. So using these 3 frames, I would like to swap in the pages one after the other into these frames. Let us start from the first page, that is 7. First it will check in the main memory, in the frames, whether the 7 is available or not. Whether the 7 is available in the frame or not. No, it is not available. Yes or no? It is not available. So it will swap in. The once it is swap in, we are considering it as page fault. So this you should note it as fault. Secondly, it will come up with a page second called 0. This 0 is going to accommodate in the second frame, right? So that is 7 is already there and 0 is going to be accommodated in the frame. Because swap in is happened, somehow you have changed your page from secondary memory into the memory, will be considered as swapping in, yes or not, as per our previous discussion. When that is happened, we are considering it as page fault. So till now 2 page faults occurred with this. Thirdly, the page number 3, that is 1, going to be trying to store into main memory. It will check whether this 1 is already available in this frame or not. 7, 0, it will check with no. So it will accommodate here. The space is there, so it is going to be accommodated. So the swap in happened. The moment when swap in happened, we consider it as page fault. So 3 page faults occurred as of now. Similarly, 2 I am trying to accommodate. 2 I am going to trying to accommodate here. Now the page replacement takes place. Now the page replacement is going to take place. See here, this 2 is trying to enter into the main memory, but there is no space at all because 7, 0, 1 occupied already. So when the new page is trying to enter into the main memory, it has to replace some existing page which is available in the main memory, right? So now the question here is, which page is going to be replaced for the new upcoming page? That is what our FIFO is talking about. First in, first out. So if you see 701, 701, which page comes first? 7, right? So 7 is going to be replaced with a new page called 2. Isn't it or not? So now it becomes 201. So now our frame size is as usual 3. We have replaced some existing first come first serve page is going to be replaced by the new page into the frame. So it becomes 201. So this is also swapped in. We have swapped in, right? So from the second memory we have swapped in. So because we have swapped in, we consider it as a page fault. So till now how many page faults occurred? 4 page faults occurred, right? Now let us see the another one, 0. So if you see the 0, 0 is trying to enter into the main memory, but if you observe clearly, this 0 is already existing in our main memory called frames. This moment we are not going to swap in anything, right? Means we call it as, this is a page hit. What we call it as? Page hit. That's the reason why this becomes as it is. 2 becomes 2, 0 becomes 0, 1 becomes 1. So this is a page hit, not page fault. This is a page hit. Very good. Next, go to another page called 3. So now, if you see, this 3 is trying to enter into what? Mainframe. So, when this 3 is trying to enter into the mainframe, which pages need to be replaced with that particular new one? Need to be synced first. So, if you see, 201, yes or not? So if you see this 201, the logic here for the FIFO is how long, the longer duration, whichever the page is holded by that particular frame is going to be replaced first. If you see the 7 3 times, right? So we have replaced that 7 with the 2. Similarly, if I want to accommodate 3, which one holds longer duration? 2 recently added. Next, 0. 0 is already existing from the long duration. 0, 0, 0, 0, 4 times. So this is the right page to be replaced with a new one, that is 3. So that's the reason why this 0 is going to be replaced with the 3. Now this 1 becomes 1. Right? So this is also going to be considered as page fault. Right? Similarly, 0 if you see, 0 is not there in this frame, 2, 3, 1. So it is going to be replaced by something else. What is that something we need to be understand here? If you see the 2, 2, 2, 3 times, 3 first time, and 1, 1, 1, 1, 4 times. So this is the right number to be replaced with a new page. So that's the reason why this 0 is replaced with the 1. So now our frame is going to be considered as 230, right? Similarly, I want to add a new page called 4. New page called 4. So this 4 I would like to place here. So where I have to place? See, already 230 is occupied, but the logic here to store FIFO is the longer time whichever the page is kept in that particular frame is going to be eliminated first. That's the logic we have to follow. See, if you see 4 to accommodate, 2 is there minimum 4 times, 1, 2, 3, 4. Now where 3 only 3 times, 0 only 1 time. So 2 is the right place to be replaced by 4. To be replaced by 4. So now my page becomes 430. Similarly, apply this for 2. So 4 already there, 3 for the longer duration, 2 and 0. Similarly, 3 you want to accommodate, 4, 2 and this 0 is longer duration, that is more than 3 times. So becomes is going to be oldest one, need to be replaced first. So 3. Similarly 0 you want to accommodate 0, 2, 3. So because 4 happened for the longer duration, so 4 is going to be replaced by 0, 2, 3. Now 3 you want to accommodate, 3 already there, this will be considered as page hit. Similarly 2 you want to accommodate, 0, 2, 3 already there, you no need to swap in anything here, so that you consider it as page hit. Similarly you want to accommodate a page called 1, 0, 1, 3. Why I have taken 2? Because 2, 2, 2, 2, 2. So many times you got 2. So the longest page holded by the frame is called 2 here. So I have eliminated that particular page called 2 by replacing 1 over here. Similarly 0, 1, 2, so on and so forth. The moment when you reach to the last reference string, you will be finding 701. Please work out on it. When you do this, how many number of page faults are going to be occurred? How to identify that? To identify that, we need to understand a formula called page. Let me use green color. It would be appropriate. So page fault ratio. If you would like to find out, then you see number of page faults occurred. How many number of page faults occurred? You have to note down. So let me write down, this is a page fault number by total number of reference string. Let me count. What is the reference string number? Starting with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there are 20 reference strings available. Denominator we have noted it as 20. Number of page faults 1, because we have stopped in 2, 3, 4. Leave this 5, 6, 7, 8, 9, 10. Leave this 11, 12. Leave this 13, 14, 15. So 15 is my page fault number. So if you try to identify this, you will be getting 1.3333 like that ratio. The ratio of the page fault ratio is going to be 1.33. Yes or not? 20, 15, 15 ones are 15, 5.0, 3s are 45, so that you will get 5, so 1.3 bar. Isn't it or not? So this is how you have to identify the page fault. Similarly, if you would like to identify page hit, the remaining are going to be considered as page hit. So page hit ratio, to know, you should know the number here. This is 1, this is 2, this is 3, this is 4, 5. So total 5. So page hit ratio, if you want to know, then what is the formula that you are using here? Number of page hit by total number of reference strings equals to the page numbers which hitted is called 5. The total number are 20. If you try to know this, you will be getting 4 exactly. 5 4s are 20, so that you will getting the 4. So this is what the ratio of the page hit. Okay, so what we understood from this? What we understood from this? The more number of page faults, if anything is producing more number of page faults, it is going to be the worst fit. The less page faults whichever the algorithm is producing will be considered as what? Less worst one. So that is called best fit. So here you kindly note down number of page faults. Page faults we are using FIFO are counted as 15. Page hit by using FIFO is called 5. Now, what is this diagram is telling? When you try to increase the number of frames, it is going to become reducing the number of page faults, right? So we will see this, whether it is true or not. We will see this with the help of a new reference string represented here in this slide. Let us see how many number of reference stages are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Total 12 reference strings are there with the help of FIFO. If we try to use 3 frames by doing all the pages replacement, you are going to finding total number of page faults are 9. When you try to increase the number of frame size from 3 to 4, it's supposed to reduce the number of page faults from 9, less than 9. But what happened with this example? It was increased into 10 page faults. So this is called as a Belody anomaly. This, according to the Belody's anomaly, more frames going to represent more page faults. This happens only for the rare case, not for all the reference strings. It is supposed to reduce the number of page faults when the number of frames are trying to increase. But very rare cases, as stated by Belody's, when you try to increase the number of frames, your page faults are going to increasing rather than decreasing. So this is an anomaly stated by the Belody's. Please understand, this is very, very important for all the competitive exams. Okay? It's a very rare case for the reference strings like this. Now we will see the another example for first in, first out. Okay? So this is according to the Belody's anomaly. What happened? When frames are 1, faults are 12. When frames are 2, faults are 12. When frames are 3, faults reduced into 9. When frames are 4, it is increased. Now again it is, so ultimately what happened here, Belody's are telling that for some references, it is no exemption. It is going to happen like this. So this is all about the first in, first out. In the further class, we are going to discussing about a few more algorithms in the page replacement algorithm. Those are nothing but a new algorithms called least recently used optimal page replacement algorithm. Like that, different new page replacement algorithms we are going to discuss now. So till now we have discussed about first in, first out page replacement algorithm, and now today we will be discussing about a new page replacement algorithm called optimal page replacement algorithm. Okay, so this optimal page replacement algorithm, how it differs from the previous first in first out algorithm. The previous first in first out algorithm. You should understand very carefully about the reference string, how it is going to be replaced with a new page into the main memory. By using this technique, today we are going to learn. Okay. So this optimal policy selects for replacement the page that will not be used for longest period of time. Please underline that. The optimal policy selects for replacement the page that will not be used for the longest period of time. In future, whichever the page is not going to be used for the longer duration, that we should consider. Okay. So impossible to implement because need to know the future. But predicting the future, which page is going to be asked by the user, we don't know initially. So theoretically it is possible, but practically it is not possible. But anyhow, let us see the procedure of the optimal replacement page replacement algorithm in this session. So in this session, we used the same reference string that we used for the FIFO. Yes or not? The same reference string, which consists of around 20 reference strings. If I apply the same reference strings here for optimal page replacement algorithm, let us see whether it is going to improvise the performance of the operating system or not. How do we know that whether it is improvising? By reducing the number of page faults. Whatever the algorithm that may be used, it should reduce the number of page faults occurred during the replacement. During the page replacement, isn't it or not? So whichever the algorithm that you are using for page replacement, if it is bringing out the less number of page faults, that's the best fit I can say. Yes or not? Let us see the policy that is followed by this optimal page replacement algorithm is, as you already know, 7 0 1 2 0 3 0 4 2 3 0 3 2 1 2 0 1 7 0 1. This is the reference string. We are considering it as pages stored in the secondary memory, right? Now this secondary memory is trying to store these values, pages, data, memory into main memory. That's called frames. The frame size is again I have taken 3 here because for the first FIFO page replacement algorithm I used 3. So let me use same size of the frames here also, that is 3. So 7 first I brought here because I found this frame is empty. I can place my page into the memory. Yes. Secondly, I have 0 page. Second position also vacant. So I can store that. This is also a page fault because I have swapped in. Thirdly, I have 1. I can replace this page into my frame 701. 701. Yes, till this point everything is crystal clear. Yes or not? Now, the question starts from here. Now when I want to store my new page called 2 into my frame, first I verify whether this 2 is already there in my frame or not. Yes, I verified 701 not matching with a new page called 2. I have to replace this because my operating system is in the need of this page. So I have to replace this page 2 by replacing some frame from my memory. Now question is which frame you are going to replace by this page is the question. According to the optimal, what it is saying, the policy is for replacement will not be used for longest period of time. Will not be used for the longest period of time. See, when I want to swap in my 2 into somewhere in my frame, I have to verify that list of frames which already exist in my main memory are going to be used further in the future or not. I have to verify as per the sequence whichever is going to be used at the end, that is going to be my replacement point for me. So let us see. If you see, this 2 is going to be accommodated by somewhere else here. I have used 7. Why? Because if you see this 7 in future, the longest period, because very recently I am not going to take up this page and there is no use for that page for me in my memory. So because I don't require this particular 7 for my upcoming activities using in my operating system. So that is the reason why this optimal page replacement is going to be verified this 701. If you see 0, after 2, my 0 is required for me. So I cannot change this 0. Whereas if you see this 1 after my 0, I can use my 1. So this 1 also useful for me when compared with the 7. Because 7 is the longest time it is going to be there. It is not going to be used very recently for me, right? So now what I am doing, this is the best appropriate action to be taken here for replacing this 7 with the 2. So that's how the optimal page replacement algorithm is going to take place. 2 is replaced by this and 0 and 1 is as it is. Now I want to add one more page called 0. This 0 is trying to enter into my frame, but it will verify whether this is already existing or not in my frame. Yes, it is there. So no need to swap in. So this cannot be called as a page fault. This can be called as a page hit. Yes or not? So that's the reason why I left it as blank. You assume that already 201 is repeated here. 201. That's all. Right, next 3 I want to replace. So if you see 2 already there, 0 is there, I replace it with 3 here by 1. Yes or not? So why I have selected 1? That's the question. If you see 2 is going to be used in future, just future. 0 is also going to be used immediately after this 3. So I cannot use this 0. I cannot even use 2 also. But whereas if you see 1 is somewhere in the last corner, that is in the middle of my reference string. Nowhere the symptoms for my replacement, for my coming activities. Right? So that's the reason why I have selected 1 here. For replacing this 3 here with the 1. So 203 is a best fit for me. So this is one page fault. You are replacing means page fault. You are not replacing means page hit. Number of page faults are increasing means the worst algorithm it is. The page replacement algorithm has to bring out an activity to reduce the number of page faults. That's the main goal of the page replacement algorithm. If you keep on continuing like this, you are going to use the same page here, that is 2, the same page that you are using 3, hit. Now 0 you want to keep because 2 is going to come very recently, 3 is going to be very recently, but whereas 4, if you see, there is no 4 at all in my reference string. But how do I know my future reference string? Practically it is not possible, right? So because this is not possible for implementation. If it is possible by the youngsters like you, if you identify a new algorithms to predict the future, then there may be a chance to implement this optimal algorithm in the operating system so that it will give a fruitful result to reduce the number of page faults. So the efficiency of the operating system will be increased more by using such algorithms called optimal, like that. Okay. So if you keep on doing like this, 2 is there, you can use 2 again, 2, 0, 3. 1 is going to be there, so 1 I replace with 3 because in coming future I don't find my 3 there, so I can use this slot for replacing my 1 here. Okay. So similarly 2 is already there, 0 is already there, 1 is already there, 7 I want to replace. With 7 what I have to replace? Because if you see this 0, after 7 I can use 0. After immediately 0 I can use my 1. So this is not going to be replaced. But whereas I can replace with 2 by keeping 7. So this is how the page replacement algorithm takes place in optimal algorithm. Okay. So this is how held for this. Now, if you you do one thing, you use the same reference string, but instead of 3 frames, you do an activity by increasing the frame size into 4 and practice it and show me in the class. Next, this is another reference string for practice purpose. You can also keep working on it with the latest reference string by 4 references frames and page faults occurs are 4. Just imagine to place 12 reference strings into my 4 frames, I got 6 page faults. Next, the very interesting algorithm called LRU, nothing but least recently used. What we call it as? Least recently used. If you look at the previous example, in future, it is looking at the future direction, optimal, for the hint purpose. Whereas for this present algorithm, LRU, you should look after previous, past. LRU is past. Let me explain you with this reference string. The same reference string I have used here for the explanation so that it will be convenient for you guys to understand more. 7 takes here, 0 takes here, 1 takes here. Now if I want to keep 2, which is recently used but least, to be replaced with a new one. That's the point you should understand. This should go in this direction. This should go in this direction. This should go in this direction, left to past. Okay, please understand. Recently used but least. Recently used but least. So 7 is the least one, so I replace this with 7. Similarly 0 already there, no need. Similarly 3 I want to use, but what I have to look after? 2, 0, 1. 2, 0, 1, which is the least one. This is 1 is the least, so I replace 1 with 3. Similarly 0 already there, hit. 4 I have to replace, 2, 0, 3. 2, 0, 3, which is the least one to be 0 already there, 3 already there, 2 already here. So this is the least, so I replace with the 2 with 4. Similarly 4. So if you keep on doing like this, how many number of page faults occurred here? Count here the highlighted portion. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. My LRU brings me 12. Yes or not? LRU, if you say the page fault ratio earlier is 15 for FIFO, for LRU 12. So it's better when compared with FIFO. So this is how the ratio is going to be calculated. Hit if you count 1, 2, 3, 4, 5, 6, 7, 8. Total 8 are there. So page hits are earlier 5, now it is 8. So this is how you are going to identify page fault ratio as well as page hit ratio. So This is how it looks like for the new reference string. That is page fault 8 you got here. So if you keep on working on it, you will be getting a lot of uh, new algorithms you are going to get. So you can keep practicing it for the least frequently used also. You can also keep practicing for circular. There are so many number of page replacement algorithms. That's all for today, guys. Thank you very much.